Okay, I'm going to start in a second. Just want to make sure everything's good. All right. Hello. Okay. So I'm going to talk about black holes as fast scramblers. This will be about a 20-25 minute presentation, hopefully, and I'll leave some time afterwards for questions. So this should only run about 25 minutes at the most. So without further ado, I want to introduce a problem to us. So um, we're going to be talking about the information paradox, and this was a question that was kind of brought up during Hawking's era with the information and black holes, because there were some problems with the kind of the conception of the idea that um, information can't be destroyed within black holes, otherwise we would be losing it completely, and um, any process must be either reversible or it must increase in entropy. And with the black holes, they thought that maybe it was going to be lost forever. Um, so we want to kind of remedy the situation a bit. And up until recently, there really wasn't any answers to this. And one of the big solutions to this during the time was this idea of fast scramblers and information mirrors. And so we're going to be talking about that for a bit. And that's actually what I'm going to be talking about today. So um, this is a paradox that it sets the stage to a story involving bits of quantum information and how they, like quantum mechanics incorporates these composite states. So we'll see this in a bit. And we also want to show that this process is it's very fast. It's um, it's it shows that black holes are the fastest scrambling um, objects in nature, and so we're going to be getting into all of that. So first, we need to start with some formalities. What is quantum information? It's a very valid question. And what is entanglement? These are two very important questions that we need to answer before we go forward, because entanglement's a fundamental to quantum mechanics. So we want to understand that a little bit better as we go on. So lastly, what are scramblers? And the easiest answer to that would be the black holes. Black holes are great scramblers because they're very hot. They're they're able to kind of take in anything and break it down to its most fundamental components. And some of the ideas in string theory were kind of postulating, well, are they is it just the strings of particles? Um, how hot is it? Like, these are very important questions to ask. But we're only going to be getting to a couple of these um, today with the amount of time I have. So first, let's go over quantum bits. You may know 0, 1 as like your computational bits. That's similar to this. We're going to be finding wave functions as states, and these states are linear combinations of unit vectors, which can be written as like a 0 or 1, or like a spin up or spin down. Um, but certain properties about these quantum bits exist, and that is that the coefficients must be normalizable. The coefficients of each unit vector must be normalizable, and so we'll have like this alpha and beta within the complex numbers, and we'll see that the probability must be normalized because the uh, the regular pure state must be normalizable. Um, Moving on, let's talk about quantum entanglement for a bit. Similarly, we will have um, this idea of quantum entanglement. So typically there are two systems in quantum entanglement. There may be more, but the idea is that they cannot be written as single particle product or tensor products. And what that means is that you cannot write it as one ket, rather. So this could be 1/2 and 0 plus 1, 1 over square root of 2, any sort of normalized thing. But the idea is in the system we cannot separate the two different possibilities because we want to say, or what quantum entanglement implies is that once you make a measurement on one particle, this immediately um, results in the uncovering of what the state of the other particle is going to be. So in this case, we can find, let's see what we have. We have the spin up and spin down, or spin down and spin up. Either of these two possibilities are likely, um, but what we know is that the sum of the two particles' spins is going to be zero. So this is an entangled state because if you make a measurement on one object, we immediately know the result on the other. And that's going to be consistent across the board, even within the whole notion of complementarity, which we're going to get into next. So just to kind of give you an idea of how we're going to be notating things for a little bit, this is a composite state that has a normalized coefficient of the size, and this is just kind of by convention what they choose, what Hayden and Preskel choose. You can write it as a tensor product of two states, but you're going to absolutely have one pertaining to one system, say a message being sent, and another being a separate system that's entangled with that message. So we can write it in any of these two ways. Just by convention, they write this as the definition of the composite state. So moving on, complementarity. This is the idea that once beyond the event horizon of a black hole, information can't be passed, because of the geometry of the black hole is so intense that light cannot pass through, and so we use crystal coordinates to describe this geometry, and that gives us our light cones, and we're going to see that in a second. So this idea led to what's known as the memory paradigm, and I've done research on this in the past and presented it, so I'm going to try and go over that briefly because this is an important next step that we're going to go through. And the memory paradigm is an extension of complementarity that says there's this stretched horizon that exists, be like a Planck length from the event horizon itself. So there's like ohmic behavior, there's it acts as a conductor, and given a charged particle, or like an electron, it disperses over the event horizon of the black hole. It disperses over the entire surface area of the black hole. And we can see that it disperses within a time frame of the log of the Schwarzschild radius of the black hole. So we're going to see that too in a bit. Just briefly, we're going to go over this coordinate system allows us to see infalling light rays. So if a person or an observer or a pulse is found at this point in spacetime, we're going to have infalling light rays and outgoing light rays, excuse me. And these are null light rays because the metric is going to be 0. And that gives us this light cone. So anything that happens with this person particle thing is going to exist within this area somewhere, and it's going to most likely be a point or like a set of points, but all that matters is that it cannot move from here in any other direction other than what is inside this light cone. So the stretched horizon, as I said before, acts as a conductor. So using Maxwell's equations and metric tensors of general relativity, we can find an expression for the electric field of a black hole. And this allows us to find a solution for the surface charge density, and that allows us to find the time span it takes for the dispersing of an electron above the strict horizon. And what you're looking at here is going to be the electric field of the particle in Rindler time, or in Rindler coordinates, and that equates to the electric field in Minkowski coordinates. And what we'll find is that it's easiest just to do it in Minkowski coordinates first, then do a coordinate transformation using these values for z and t, so this position and time, approximated to a very large Rindler time. And what you'll find is an expression for the surface charge density in terms of Rindler coordinates. And using this and the fact that surface charge density is like the charge over the surface area of the black hole, we can solve for this Rindler time, so that way we get the time taking on the order of the log of the Schwarzschild radius. Okay, so now we're going to talk about this kind of thought experiment that's kind of posed by Hayden and Preskill. And this is going to kind of incorporate everything that we've had thus far. And I think we're doing good on time, so I'm going to kind of think a little bit about what I want to say next. So we have this whole experiment here, and this is kind of there's a lot going on within this picture, so I'm going to try and break it down as I go, and talk a little bit about each of the features of the reading that they kind of pose to us. So initially, there's three actors. There's an Alice, there's a Bob, there's a Charlie. Charlie acts as a reference system, so he's just kind of chilling out here. We have Alice, which sends her message into the black hole as opposed to just jumping in, kind of careless. Then we have Bob, and he's been kind of observing the emitted radiation of the black hole throughout most of time, or through most of the lifespan of a black hole, which just kind of entertain the idea for a second, because it doesn't really make sense to do that, but we're going to see why in a little bit, I guess. So assuming Bob has total control of the black hole and its emitted radiation, Alice throws in her message into the black hole, and her message is entangled with Charlie's kind of reference system, and that kind of means that the reference system has the same dimension and like the number of qubits that it has, and what they kind of posit is that the black hole has this n minus k qubits, you can say, like n being some number, k being some smaller number, and without the message it has n minus k. With the message it has now that plus k from the message, so it equals out to a nice n qubits. With the randomization, we will kind of bring up a little bit later why this S is here, but essentially what this says is like Bob is going to be looking for something of size k plus some smaller amount, some extra bit of information. And that will kind of help them, as they kind of explained, that'll kind of help them like decode things within a timely manner, I guess. So Bob waits for S bits to come out after the black hole actually ends up scrambling this information. This allows us to actually say, though, that because N and M were entangled, M being maximally entangled with the black hole at this point allows for the black hole to be maximally entangled with N. So that's important for this graph too. So we need to bring up this idea of unitary transformations. So we need to assume that the internal dynamics of the black hole are deterministic and unitary. So they can be reversible, and we can get something back from that. Otherwise, the entire point of solving this information pair puzzle would have been kind of moot. But so we're going to see that this Mn is now entangled with this Bn, B prime n, and now we're going to kind of introduce this idea of density operators, which gives us the original composite states in terms of like some matrix. And so what they end up doing, and what I would like to go into further, is seeing how these density matrix actually can transform using these density operators, because with these density operators we can actually observe that they can serve as observables for us. So for each of these density operators, we'll find like a form generally on the you can replace these like m and n with like in this case n and b prime, and what ends up happening is we use these density operators with the unitary transformation in a way that transforms the density operator that then goes back to the composite state, which has this entangled set of quantum information. So it's a neat little package that allows us to kind of say, all right, this is now transformed into something, some other operator, which gives us another observable that Bob can then use to encode things differently. So that's going to be interesting. So Fast Scramblers is a paper that was written by Susskind and Sekino back in 2008, and right in the beginning of it, they kind of established and say that any subsystem will be extremely close to thermal for any m degrees of freedom less than the entirety of the degrees of freedom of the system, less than half of the entire degrees of freedom of the system, I bet. So when this condition is achieved, for example, any subsystem smaller than half the whole system has maximum entanglement entropy, which we will call then the system scrambled. So this idea of having like an infinite dimensional system will give us like that many dimensions of the system, but the entanglement entropy is all that matters in this situation, because once we have half of the entirety of the maximum entanglement entropy, then we can use a smaller subsystem to kind of decode whatever is being scrambled, and that's what Bob will end up doing with his decoder. And once we hit that halfway point of the maximum entanglement entropy, we call that the page time. And from the page time, we will say that Bob is able to immediately retrieve the information being scrambled by Alice's message, or being scrambled by the black hole. And Bob just has to look out for this size S, this S equals K plus C sized data set. So he's going to be on the lookout for that immediately after. Otherwise, he would have to wait for the maximum entanglement entropy to deplete to half of the entanglement entropy of the lifespan of the black hole, and that might take a while. But I mean, he'd be used to it. But assuming that Alice has deposited her message into the black hole, we can say that Bob will be able to immediately retrieve it, and we would go over that after. I didn't put it in this slide set, but what would end up happening is it would scramble at the same rate as it would for it to dissipate in a charge over the black hole, and that's kind of another point that Susskind and Sekino made in Fast Scramblers. And that's kind of like the crux of the of the whole idea of fastest scrambling nature, fastest scrambling objects in nature. So this process of retrieval is going to kind of take some explaining, and it's going to take a second because there's a lot going on here specifically. So past the page time, Bob only needs to observe S qubits. Since he has already observed more than half of the bits found in E, that's the emitted radiation, and in this diagram, all of the emitted radiation that would be going out is just concentrated at here. But imagining that he has full control over the emitted radiation, he can be on the lookout for this R. So B is the black hole. It's maximally entangled with N and E, so that's kind of illustrated here. M is now part of R, so R is a larger size. It's about the size S, as I said before, and that's going to be, it's going to have that scrambled message. So N is now maximally entangled with R, and we will call, yep, and it was once part of B, and so this transformation is applied on B, hence R is chosen. So B prime now has minus S bits, and over time the entanglement entropy of the entanglement of B prime and N gradually weakens. So I didn't draw that there. Bob interprets R, compares it to the size of N, and he begins decoding the qubits. This is kind of a very hand-wavy gesture for kind of describing what's going on the retrieval process. There's a lot more theory involved with the quantum information aspects of this research done in Hayden and Presco's paper, but I, would probably need a little bit more time to kind of go over that, and all that really matters in terms of like understanding the transformation, the unitary transformations, is understanding that it is unitary and that it is reversible, like the process is reversible and you can get back to this original density operator. And these maximally entangled systems must be near maximally entangled for Bob to be able to decode within the proper time spans that I've kind of illustrated. And so here I will probably add something here to kind of show or illustrate later on that the scrambling time is kind of on the order of the retrieval time of the, well, not so much the retrieval time, but it's on the same order as the dissipative time needed for the electron to dissipate over the structure horizon of the black hole. So trying to think of any questions that might come up. I'll probably clean this up a bit, and I will definitely entertain any questions within the remaining time in it, because I have it's just under 25 minutes, so I need to take it slower because I'm going a little fast. But other than that, I think I covered a lot of the main points. So yeah, I think that'll do. In summary, we'll see the thermalization of the black hole. I gotta watch my ums too. Gotta watch my ums. We'll see the thermalization of the black hole happen over the time span of the log of the Schwarzschild radius, and I think it'd be interesting to see just how how it might actually be illustrated, like if it could be modeled in real time, I guess. Because because you can write Rindler time in terms of coordinate time, or Minkowski coordinate time. So that'd be something to do for the future, for sure. Okay, let me know what you think.